Alright, so this is about a graph 9.3. So what's graphs? Graph, like we have a node that has the path, and they're all linked together. You can look at graph like we have a city here. City has a street, and this is a street that's going to connect between the cities. You can go from city A to B by using this one street linking, or you can just go to city C first and drive back to B. So it's like network. This is graphs. So graph is a data structure that consists of a set of nodes and a set of edges that relate the nodes to each other. So what's edges? Edges we call arcs, or arcs, a pair of vertices representing a connection between two nodes in a graph, just like a street I compared to. So vertex. Vertex is a node in the graph we call vertex. So that means graph composed of vertex and edge. We have undirected graph, that means two-way street. If we have directed graph, that means it has to be go in one direction, one-way street. So let's look at the image. Undirected graph, you can either travel A to B or B to A, which is fine because it's two-way street, no directions. But if you do directed 11 to 1, you cannot do 1 to 11 because it's one-way street. If you want to do that, you have to create two vertices, right? 1, 3, and 3, 1. Now come back to how would you write the expression to represent a graph. So in math, we just say G equals to graph equals to a set, right, of V. This is the vertices, and E, a set of E, is the edges, right, where V is a finite non-empty set of vertices. E is a set of edges written as pairs of vertices. Now let's see how we're going to write that. For example, this is undirected graph. We say V graph 1, this name is graph 1, equals to a set of A, B, C, D. So those are a set of vertices. And E is the set of the edges for graph 1. AB, right, this is the edge AB, AD, and BC and BD. Now, for directed graph, same V is a set of graph 2. We have 1, 3, 5, 7, 9, 11. Those are vertices. And E is a set of the directed 1, 3, and 3, 1 edges. 11, 1, right? 5, 7, 5, 9, 9, 11, and 9, 9 self. So that's how we represent in the mathematical expressions or formula of sets, set of vertices and set of edges, and use the value pairs to represent the edges. Graph 3. This is like a binary tree, right? BST. BST technically is a graph. It is a directed graph with all the nodes and all the edges. Adjacent vertices. Two vertices in a graph that are connected by an edge, we call adjacent vertices, like or the neighbor city, right? Like Arlington is where adjacent vertices to Washington DC, or Falls Church. path, a sequence of vertices that connects two nodes in a graph. Complete graph, a graph in which every vertex is directly connected to every other vertex. Weighted graph, a graph in which each edge carries a value. So for example, like we said, complete graph, all of them, right, for directed, they have the way connected all together to all the nodes. Same as undirected, they all connect directly to all the nodes. This is called complete graphs. Weighted graph, so they have the wage. Like, in order to travel from Austin to Dallas, this could be the wage. It could be the price of the ticket. It could be the time to travel. It could be the distance to travel, like 200. Right? It can be more than one wage. Like this one just show you just one. Now based on this, you can use the ways to make the efficiencies to find the shortest path, cheapest path, most efficiency path. So now we understand what's a graph. So we can look at the ADT. So what kind of operations that we need on a graph? So many other operations on a graph can be defined, but we're going to choose just the one that's useful for the graph application. So let's look at WeightedGraph.interface. So we always use interface to define our operation, or ADT here. Is empty, is full. Add vertex, just like we add the new node, right? Add vertex, same thing. Has vertex, it already has that vertex, already contains it. But now we also have to add the edge. And we have the wage. We can consider to have wage is between form and 2. And get 2 vertices. So we can have a vertex in. Right? So we want to see it's going to return all the possible vertices that are adjacent to that vertex. And when we do traveling through the vertices in the graph, we may want to mark the vertex that we visit. And we can check is it marked already. And we should be able to get clear the marks that we mark. And also get the unmarked. Return an unmarked vertex if any exists, otherwise returns no. So this pretty much is used when we do traversal, right inside the graph. So we can use array to implement and linked list approach to or reference approach. So let's look at array-based implementation. The density matrix for a graph with n nodes, an n by n table that shows the existence of all edges in the graph. So with this approach, a graph consists of an integer variable's number vertices, the number of vertices, right? A one-dimensional array for vertices, and two-dimensional array for edges. Like we want to use array to implement graph, we said, Okay, we have number of vertices to keep tracking how many vertices already add into the graph. And we just use one-dimensional array just to keep track all the vertices, and two-dimensional arrays to do all the edges between the vertices. So let's say we're going to use this example to create a graph. So we have 1, 2, 3, 4, 5, 6, 7 vertices. We're going to create an array to store that with, now we have number of vertices equal to 7, and one-dimensional arrays to store all the vertices. And we're going to do two-dimensional arrays to create a weight edges. Edges that store the weight. When there's a weight, that means there's edges. When there's no weight, then there's no edges between the vertices. Like for example, 0 Atlanta, 2 5, which is Houston, is weight is 800. We use two-dimensional array to help. So go back. Here you go, right? It said what? Atlanta to Houston 800. Atlanta also go to Washington 600. So we have to do node Washington is node 6 and 600. So that's we pretty much implementing the graph using two arrays, one-dimensional for vertices, two-dimensional for edges. And with 0, that means there's no edges between those two vertices. When it wedges, then those are the edges for vertices. Alright, so let's look at the implementation now. So we can call a class named WeightedGraph, which is implemented WeightedGraph.interface using an array. So we just create the null h equal to 0. So that means this represents no edges between those vertices. Default cap size of your array 50. Number of vertices, keep tracking on how many vertices so far in the graph, and max vertices. So the maximum that we can go depending on the size, right, of array. And an array of vertices, one-dimensional array, which is a T generates. And this is an int, two-dimensional arrays, which is edges. And since we said when we do traversal, we have to make sure that we mark if the vertex is already visited. So we create an array one-dimensional to keep tracking on the vertices as marked. Now let's look at the constructor. We might just initialize the number of vertices to 0, max vertices to the size of the cap array. And this is an array of objects, so in generics we have to casting back and use object to help create the vertices, which is the size depending on the decap, the default cap. Marked. Now we create an array is the Boolean because keep tracking on if we visited our vertices or not, and the array two-dimensional array for the edges based on their size, default caps. So the constructor with no parameters, right? And this is with parameters. So instead of default cap, we just replace with max v. That's the size. Add vertex. Now we pass the vertex to add. So add vertex to this graph. So when we start to add vertex, we already have number of vertices, keep tracking the index. So after we add, we increment the non-vertices. Put the vertex in.